So welcome to part 2 for section 2.4. In this video, I'm going to try to keep it, again, relatively short. We're going to focus just on the transpose matrix and how to transpose a matrix. And then in the final video, trying to break this up into 3 sections, kind of like normal, we'll look at what a symmetric matrix is. Now, some of the examples I'm going to leave as exercises. A lot of the proving for the sum, product, and inverse for transpose matrices, I'm going to leave as exercises. I will show a couple of examples, but otherwise I'm going to save that in terms of for you to kind of work through and try to justify and prove, again, as practice, as part of problem sets, and potentially as a summative for this ended unit problem set. Now, when we want to transpose a matrix, I mentioned this earlier when we talked about permutations. When I transpose, the idea is that when I take a matrix for A, any ij entry gets swapped when I transpose into the ji. So in other words, the columns and rows are changing. Another way to think about it is that if I have a matrix for A and I have numbers here along the main diagonal, when I transpose a matrix, the main diagonal would stay the same. And what does flip are these entries here, opposite of, etc. This is really bad. Opposite of the main diagonal. So these 2 entries would swap, these 2 entries would swap, these 2 entries would swap. Because you are literally changing the rows of a matrix and making them the columns for a transpose. And so he gives an example at the beginning of this kind of section here where A is equal to, I believe he gives a 2x3 example, 1, 0, 2, 0, 3, 4. And so if I want to transpose this, notice that if rows and columns are swapping, that means the dimensions themselves are also swapping. A transpose will be a 3x2. So when I do all of these swappings, the 1, 1 entry would stay the same, the 2, 2 entry would stay the same, but now the 2, 1 becomes the 1, 2. The 1, 2 becomes the 2, 1, etc. Row 1 becomes column 1. Row 2 becomes column 2. And I think that's like the easiest way to essentially try to think about it. Now, when you're doing these transposes, and he gets into some MATLAB notation, so depending on who you are and if you're in college, typically if you're an undergrad, you take at least 1 course in computer programming where you get to choose either between C++ or C++ and MATLAB. And I took MATLAB. Many math majors, engineering majors tend to take MATLAB or bounce into C++. But I think in the end, like I traditionally would use Maple software to work in, especially as I got into my master's program in solving matrices and differential equations. So he gets some notation for MATLAB where instead of using a T for A transpose, they use an apostrophe, so almost like an exaggerated prime symbol for the derivative. And so he kind of mentions that. I think the biggest thing that I want to, just again, kind of highlight, just like with permutations, just to kind of make some talking points on, is a couple rules when it comes to transposes and as I'm adding matrices, multiplying matrices, when I want to apply the transpose, is there a formula, a template, a relationship between the operations and what we have? So, for example, if I have 2 matrices, A plus B, and I want to find the transpose of this, and I'll just kind of let this arrow represent transposing. It turns out that the transpose is literally AT plus BT. If we transpose the individual matrices and then add those results, we actually get the same result as just transposing the original sum. And we could give a really quick example, like if A is 1, 6, 0, 1, this is something that he gives a little bit later on. A transpose, let's call it, we need another matrix for B, sorry. Let's say B is 1, 1, 1, 2, for example. A transpose would be 1, 6, 0, 1. B transpose would be 1, 2, 1, 1. So if I go through and I add A and B together, I would get A plus B is 1 and 1, so that's 2. 6 and 2 is 8. 1 and 2. So that means if I transpose A plus B, I'll write it up here, I would get the matrix main diagonal 2 and 2, 8 and 1 would swap places. But notice if I just add A transpose and B transpose, 1 and 1 makes 2, 1 and 1 makes 2, 6 and 2 make 8, and then 0 and 1 make 1. So you can kind of see this property holding for 2x2s, and again, I'll leave it as an exercise to prove this in general. But we have that first property. The first property is pretty straightforward. Nothing really interesting comes about from that one. Really, where it kind of gets interesting and we start to see some patterns is if I want to transpose a product of matrices. So if I have A times B and I want to transpose this, it turns out, just like with inverses, we can transpose B and then multiply it with the transpose of A. And then there's the order swaps. And then we can apply the transposes individually and then multiply that result. And so that this case is true. For the inverse, so if I have a matrix A and I want to find its inverse, if I want to transpose that, it turns out that this is equal to the transpose of A and taking the inverse of that result. So it's almost, and it's not directly equivalent. This is where my improper mathematics and formal language, I'm very informal, kind of as you can tell. It's very much like the properties of exponents, that these things essentially can swap places and that the operations themselves are equivalent. Very similar to you can square something and then cube it, or cube it and square it. The result is always the same. So how we apply the inverse and then how we apply the transpose is true. Now, I'm just going to show examples of these two, just like what we did with the first one. So I'm going to erase these and then kind of showcase one that he shows in the book. Again, I'm going to leave it as an exercise. Now, he walks through the cases for this one and walks through the cases a little bit for this one in terms of a proof, but I'm going to leave that again as an exercise for you to think about and kind of think through. Instead, just kind of showcase through one specific example and expand that to make it universal, which is not a great way to prove things, but just kind of showcase to you like how it kind of works before we move into inner products. So he gives the example of A being equal to the matrix 1, 0, I believe 1, 1, and then B is the matrix 5, 0, 4, 1. So again, kind of staying in the 2x2 range. If I multiply A and B together, I would get the first row staying the same, so 5, 0. And then the second row being found by adding the first two rows together. So 5 and 4 give me 9, 0 and 1 there. So my product is 5, 0, 9, 1, which means if I transpose this product, we would get the matrix 5, 9, 0, 1. Again, main diagonal stays the same. The only thing that's swapping are the entries around that main diagonal. Again, almost essentially perpendicular to the main diagonal. Now, if we were to transpose these matrices first, and then make sure that we multiply in the correct order of B transpose A, transpose. B transpose would be 5, 4, 0, 1. A transpose, flipping that 1, 1, 0, 1. When I do this multiplication in this order, 5, 4, I get 5. Over there, 5. Doing the second entry, 5 and 4 make 9. So you can see how these two statements are equivalent. 0, 1, in other words, the second row will stay the same. And so that matches. So this is indeed equal to B transpose A transpose. And again, he gives kind of a proof that starts with the most basic thing that B can be, which is a single vector, and then builds it up into a greater case. But here's a kind of a 2x2 to kind of back that up. And I'll leave the transpose of the inverse in there so you can kind of read through his example. But I think just kind of showcasing this one will hopefully be enough. The last thing that I wanted to hit on, because coming from the realm of applied mathematics, and him kind of touching on it here, really kind of shows you the foundation that linear algebra can set because of where we see it. is really kind of bringing back this conversation of inner products and outer products. And he states that, you know, when we talk about the inner product of a matrix and saying x, essentially x dot y, like when we're doing this, he does not like the notation of the dot. And honestly, it's not great because of how we use the dot for basic multiplication and not doing dot products and things like that. And so what it turns out is that using the transpose notation is actually a better notation of what we're doing. Because in the end, if the t is on the inside, then what we're calculating is an inner product. If I can spell product. Where we're taking something that might be a 1 by n, or essentially a 1 by n matrix, or vector, and multiplying, excuse me, with an n by 1, one column. Now, this again would swap because if x is n by 1, like if it's a single column vector, the transpose is swapping that. So when I do the multiplication in this order, notice that our answer is a 1 by 1. We get a singular number there for the inner product. And so the transpose notation, this actually gives us a much cleaner way of representing the inner product. Well, when we talk about outer products, and we've seen this in rewriting matrices, and thinking about how this works, that is when the transpose is actually found on the outside. So when I multiply x and then y transpose, we're now taking an n by 1, and we're multiplying this by a 1 by n. And notice how this leaves us then with an n by n. The result of the outer product is a matrix. And specifically, we saw this with a lot of rank 1 matrices when we're going through. And he gives a couple of examples how this connects with quantum mechanics. He talks about how this connects with mechanics, circuits, economics, and just how it, you know, is the foundation for a lot of these applied sciences that essentially are based in this in terms of inner products and outer products. So he gives a couple proofs there, and I'm going to leave it's pretty straightforward in example 1. And if you're interested in kind of the application for calculus, you can see that in example 2. And so this is where I'll kind of leave off when it comes to transposes and a couple of ways that we'll kind of see it. Really kind of a basic definition as we continue into the text and into the course structure. In our final video for Unit 2 before we, really final video for Unit 2 and 2.4, we'll take a look at what's defined as a symmetric matrix. He gives a good transition from the calculus derivatives into this. And then we'll look at symmetric inverses and what this idea is and how they're connected to the transpose. AKA the driving question is what if the transpose of a matrix is the matrix? Even if I swap rows and columns, it's still the same matrix. And thus, by definition, symmetry. And so we'll get into symmetric matrices. We'll look at some of that. That's going to be really important for some factorizations and diagonal matrices. Again, very short video. We'll keep it pretty concise. I think this one was only maybe about 15 minutes without looking at my phone time. So we'll do one more, and then we'll be done with Unit 2.